Great skill is needed by a melter to make good steel. He must watch for the signs which show how the furnace is behaving and make the adjustments necessary to keep it operating in the most efficient way. Experience can teach his eyes to weigh up these signs and his hands to make the right adjustments. But the standard can be improved by the use of instruments to help his eyes and automatic controls to help his hands. In this film, we'll show how some of the most important of these devices are used. Throughout the charging period, the melter sets the flame burning hard in order to raise the temperature of the bath as fast as possible. But he must remember the maximum temperature the roof can stand, and so must keep the gas supply within limits. If the flame is too hot, the roof may melt. He keeps an eye on the roof, and nowadays he has a temperature gauge on the instrument panel to help keep a check on the roof temperature. Notice the marker at about 1650 degrees centigrade. That's the top temperature he can allow a silica furnace roof to reach. The indicator on the instrument panel is connected to a thermometer, or pyrometer as it's called, at the back of the furnace. The gauge is worked electrically, so the two are connected by wires. This is all you can see of the pyrometer when it's fitted to the furnace. It's inside a casing to protect it from dust and heat. A telescope in it focuses the heat from the roof onto a heat-sensitive part. Incidentally, the melter will still have to keep an eye on the roof, as the temperature is only read at one small spot. If the melter sees that the roof temperature is on the high side, he must lower it by reducing the flame inside the furnace. He does this by altering the gas valve, and so cutting down the producer gas supply to the furnace. Here he's doing it by hand, but it's possible to arrange the temperature indicator itself to operate the valve. This is the principle of automatic control. The technical details can be complicated, but the principle is simple. Suppose we arrange for electrical contacts to be placed on the temperature indicator like this. Now, when the needle rises to the highest safe temperature, the contacts touch and an electric current can flow. This current can work an electric motor, and the motor in turn can operate a gas valve, cutting down the gas supply to the furnace. The reduced gas supply will allow the furnace to cool down, and as the furnace cools, the indicator will fall and the contact will break, stopping the motor. To complete the control system, there must be another contact just below the safe temperature, which will make the gas valve open again when the furnace temperature gets too low. A system like this can ensure that the furnace is always near the correct temperature. All automatic control systems have these points in common. They all have a detector corresponding to the furnace man's eye, an instrument which corresponds to his brain, which works a motor or servo mechanism corresponding to his hand. We can take another example. The melter keeps a slight pressure inside the furnace to make sure that cold air doesn't leak in. He can estimate this pressure by the flames which blow out around the doors. This is called the sting. Also on the instrument panel, there's a pressure gauge which indicates the furnace pressure. The pressure gauge is connected by a pipe to the roof of the furnace. This is the point where the pressure is measured. The pressure is recorded in inches of water. To understand what is meant by pressure being measured in inches of water, let's look at this U-shaped tube with some water in it. The level of water is the same in each arm, because the pressure in each arm is the same. If the demonstrator blows gently down one arm, the level of water will fall in that arm and rise in the other. The difference in height of the two columns is now 2 inches. Now we can say that the demonstrator is blowing with a pressure of 2 inches of water. Modern instruments don't usually employ U-tubes, but they are still calibrated in inches of water. The pressure in the furnace is very small by comparison. It's measured in hundredths of an inch. It's usually between 3 and 600ths of an inch of water. If the melter needs to alter the furnace pressure, he does it by adjusting the damper in the furnace chimney. The action of the furnace damper is the same as the damper on a stove. A metal plate can be pushed into the stovepipe to shut off some of the draft from the chimney. In the same way, the furnace damper is closed to lower the chimney draft and so raise the pressure inside the furnace. By an arrangement similar to the one used with the roof pyrometer, the furnace pressure can be controlled automatically. In this case, the indicator on the pressure gauge is made to work a servo mechanism which operates the stack damper. Once again, we have the elements which correspond to eye, brain, and hand. To keep a furnace working efficiently, it's essential to have a flame of the right type. Looking through colored glasses, the melter can judge when conditions are right by the length of the flame and its general appearance. To get the flame quality he needs, he must be able to control the amounts of both gas and air flowing into the furnace. He does this by opening and closing valves in the gas and air mains. To help him to estimate the correct mixture, there are 2 meters on the instrument panel, one of which shows gas flow and the other air flow. The gas flow meter is connected to a point on the main producer gas supply pipe, where the flow of gas is measured. And the airflow meter is connected to the main air supply pipe, where the flow of air is measured. Having adjusted the gas and air flow, the melter checks the roof temperature to make sure it's below the danger level. At the same time, he checks the furnace pressure gauge, because altering the gas and air will of course alter the furnace pressure, but in this case not enough to need any change of the damper setting. It's now time to check the reversal of airflow and gas flow. You remember how the system of regeneration works with 2 sets of heating chambers. At the top of each of the chambers heating the air, there's a pyrometer measuring the temperature. Each pyrometer is connected to a temperature gauge on the instrument panel. At the moment before reversal, supposing set 1 has been heating the gas and air, it will now be the cooler, and its temperature gauge will be reading about 900 degrees centigrade. Set 2 has been heated by the burnt gases, so will be hotter, its gauge reading about 1200 degrees centigrade. The temperatures are also recorded on a moving strip of paper. Every few seconds, a pen attached to the indicator makes a dot on the paper. The paper moves on so that a line of dots is drawn. The indicator records the temperature first of one set of checker chambers and then of the other, so that the pattern shows what's happening at both ends. If we draw the temperature of one checker chamber, say number 2, it will rise from 900 to 1200 degrees centigrade during 20 minutes. Then the furnace is reversed, and the temperature falls back to 900 degrees during the next 20 minutes, making a wavy line on the paper. The temperature of the other chamber, number 1, drawn on the same sheet, will start at 1200 and drop to 900. So that the 2 lines cross every 20 minutes and make a regular pattern. This is the sort of pattern a melter wants to see. In practice, the pattern is never quite so regular as we've shown. If the pattern is irregular, as it is here, then he must allow one side more time to heat and change over at irregular intervals until the two sets of chambers are heating and cooling evenly. The roof temperature is also usually recorded on a chart. From a typical roof temperature chart, you can read off the progress of the melt. Each time a charge goes into the furnace, the temperature drops, so the line falls and rises steeply. Then, during melting, the temperature remains fairly steady at a high level. It drops while additions are made during refining, and then keeps steady until tapping. So far, the instruments have been helping the melter to control the running of the furnace. But the running of the furnace alone won't make steel. The melter sends frequent slag and metal samples to the laboratory, and at certain times, particularly before starting the boil or tapping, it's most important for him to know the temperature of the steel bar. To measure this, he uses an immersion pyrometer. It's called an immersion pyrometer because it's immersed or dipped into the steel bath. It can be dipped into the bath only for a few seconds without melting. It measures the temperature electrically and records it on a dial. The tapping temperature is around 1600 degrees centigrade. We've now covered all the main instruments on an instrument panel, as well as the immersion pyrometer. Each makes its own contribution to the efficient running of the furnace. Let's run over them again. The furnace pressure is measured by a gauge in the furnace roof connected to the indicator by a tube. An electrically connected pyrometer registers the roof temperature. Both these instruments are often used for automatic control. The furnace pressure can regulate the stack damper. The roof temperature can regulate the fuel supply. With gas fuel, the flow is measured in the gas main from the producer to the furnace. The airflow is measured in the main air intake pipe. Finally, two temperature gauges record the temperatures at the top of the two air checker chambers. Other measurements are sometimes made, but these are the most important instruments. A board of this type can show accurately at a glance how the furnace is behaving. With the help of these instruments, the furnace can be worked faster and will produce steel more efficiently.